Okay, this is the last section of chapter 7. We're going to discuss machines and uh, sources of energy, alternate sources of energy, but we'll start with machines. Let me dismiss my image. And machines are is a machine is a device for multiplying forces or changing the direction of forces. You cannot create energy, but you can transform energy from one form to another or transfer energy from one location to another. You cannot multiply work or energy. We can see that, in electricity and electronics, you have step up and step down transformers where you can take 120 volts and step it down to 5 volts, and or you could step it up. You could step up 120 volts up to 20,000 volts, but your current is going to be much less. And with the power in is going to be the power out. You can't get something for nothing. So there's always a trade-off, and we'll see that in like levers and stuff. Um, okay, principle of machine is a conservation of energy concept. The work input equals the work output. The input force times the input distance is equal to the output force times the output distance. So force times distance input is equal to force times distance output. Now, so if the force goes up on this side, um, or let's say, given this, the force goes up, the distance is going to have to go down. We'll see that. And here it is. The simplest machine is a lever. It rotates on a point of support called the fulcrum. This is the fulcrum. It allows a small force over a large distance to induce a large force over a short distance. So you can push on this with little force, but you're going to have a large distance. And so you're able to move something a small distance with a heavy force. So small force times big distance equals big force times little distance. That's the key takeaway from here. You're gonna the force times distance is gonna equal the same. So you decrease the force so that you don't have to push as much. You have to go a long distance to get on the other side an equivalent large force, but a small distance. Okay. A pulley operates like a lever with equal arms. It changes the direction of the input force, um, but then it can operate as a system of pulleys, block and tackle. It multiplies the force. In this arrangement, the load can be lifted with an input force half the weight of the load. So it does reduce it. Okay. Using an ideal pulley system, a woman lifts 100 Newton crate by pulling a rope downward with a force of 25 newtons. So you can see a 4-to-1 ratio there. 100 Newton crate, 25 newtons of force. For every 1 meter length of rope she pulls downward, the crate rises 50 centimeters, 45 centimeters, 25 centimeters, or none of the above. Well, if we look at this 4-to-1 ratio, it's going to have to be a one. There's going to have to be an opposite 4-to-1 ratio. So for every 1 meter, she's going to lift it only 25 centimeters. Work in equals work out. Force times distance in equals force times distance out. So 25 newtons times 1 meter equals 100 newtons times the distance out. Well, if we divide both sides by 100, 25 newtons divided by 100 newtons is 1/4. So it's a 1/4 distance. So it's 25 centimeters. Okay. Now, that's it for machines. Now we're going to go to efficiency. Efficiency is the percentage of work put into a machine that is converted into useful work output. In equation form, the efficiency is the useful energy output divided by the total energy input. And we're going to discover that there is no perfect efficiency. All machines lose because of friction, because of any number of things that you lose efficiency. There's no 100% efficiency. A certain machine is 30% efficient. This means that the machine will convert 30% of the energy into useful work, and 70% of the energy will be wasted. Be 70% of the energy input to useful work, 30% of the energy input will be wasted. 30% of the energy is input into heat, or none of the above. Well, it's A. It's only 30% efficient. 30% of the energy is input to useful work. 70% of the energy will be wasted. If you have a light bulb, an old incandescent bulb, you know that when you had to turn it off before using it, because it was very inefficient. A lot of the energy, besides giving light, would go into heating the bulb, and that's wasteful. You can see the LED lights. You can grab those pretty much after you turn off the light. They don't heat up. If they heat up at all, it's not anywhere near that of an incandescent bulb. Okay, recycled energy, reemployment of energy that otherwise would be wasted. Edison used heat from his power plant in New York City to heat buildings. Typical power plants waste about 30% of their energy to heat because they are built away from the buildings and other places that use heat. Energy for life. The human body is a machine, so it needs energy. Our cells feed on hydrocarbons that release energy when they react with oxygen, just like gasoline burned in an automobile. There's more energy stored in food than in the products after metabolism. Okay, sources of energy. The sun. I mean, if you here in South Texas, we've just experienced many days of plus 100-degree weather. You can tell that there's, I mean, just stepping from direct sunlight into shade, you can feel the drop in energy. The sun puts out a lot of energy. The sunlight evaporates water, water falls as rain, rain flows into the rivers and into generator turbines, then back to the sea to repeat the cycle. Sunlight can be transformed into electricity by photovoltaic cells. Wind power turns generator turbines. These are on commerce between Callahan and military. There's a whole I'm going to guess it's a couple of acres. I don't really know the size of it, but you can see there's a lot of solar panels that are there on commerce between Callahan and what did I say? Military drive. Sunlight can be transformed into electricity by photovoltaic cells. That's what we were talking about. And wind power turns generator turbines. I'd already read those. I apologize. Okay. Photovoltaic cells on solar panels catch the solar energy and convert it to electricity. More energy from the sun hits Earth in 1 hour than all of the energy consumed by humans in an entire year. That's how much energy we get from the sun. Okay, fuel cells. The fuel cell runs opposite to the battery shown, whereas electricity separates water into hydrogen and oxygen. In a fuel cell, the hydrogen and oxygen are compressed at electrodes, and electric current is produced at the electrodes. This is figure. Oh, I lost it. I missed my place in the book. It's figure 725, and they go through other sources of energy. I'm not going to take the time to do it here. You can do it in section 7.9 of your book. They talk about solar power, which we just discussed. And I'm fighting with my cat over the book. She wants to lie on the book, but I need to read it. Hydroelectric power. I mean, have you ever been to Hoover Dam? That's a hydroelectric station. The water turns the turbines, and the turbines generate electricity by moving wires in the presence of a magnet. Fossil fuels, coal and petroleum. It's what we use in our automobiles unless you have a fully electric vehicle, but the electricity has to come from somewhere, and a lot of times it's from coal burning plants. Wind, if you've ever been to down on the way to Harlingen or over on uh, West Texas as you head to Lubbock, um, or I guess that's more North Texas, you'll see these old wind farms where there's a lot of these turbines. Um, and there's nuclear fuels and geothermal energy, the different sources of energy that are available. Uh, Nuclear power is the nuclear energy is stored in uranium and plutonium. The problem is what to do with the waste once the nuclear fuel is spent. Um, Byproduct is geothermal energy held in underground um, reservoirs of hot water to provide steam that can drive turbo generators. Um, Dry rock geothermal power is a producer of electricity. Water is put into cavities in deep, dry, hot rock. Water turns to steam and reaches a turbine at the surface. After exiting the turbine, it is returned to the cavity for reuse. And that's the end. That's the end of the section 4. That's the end of the chapter. Okay.